Every single second, all around you, there's this invisible language being spoken. It's the language of transformation, of creation, even decay. Today, we're going to learn how to read it. We're decoding chemical reactions. So, think about this for a second. What do sour milk, a rusty pan, and, well, even just breathing all have in common? I mean, you've got milk left out on a hot day, an old pan sitting in the sink, and the simple act of taking a breath. These seem totally unrelated, don't they? But they're all connected by a fundamental process. Well, that invisible thread connecting them all, they are all chemical reactions. It's this process where one thing becomes something totally new. And here's the cool part, it's not just random chaos. These changes, they follow a really precise set of rules, almost like a grammar. And once you learn that grammar, you can start to, read the world in a whole new way. It's pretty amazing. All right, so here's our game plan. We're going to start with how to even spot a chemical reaction. Then we'll get into the language of chemistry itself. We'll cover the big rules of the reaction, look at 4 essential types, and then wrap it all up by seeing how this stuff pops up in your daily life. Okay, so section 1, spotting a chemical reaction. First things first, right? How do we even know a reaction is happening? What are the dead giveaways? So you got to think of yourself as a chemical detective on the lookout for clues. And there are really 4 big ones. First, a change in state, like a liquid turning into a gas. Did something change color all of a sudden? Are there bubbles fizzing up? Or maybe the temperature changed. Did the thing get hot or maybe even cold? Any of those, that's a telltale sign that a chemical transformation is going down. All right, section 2, the language of chemistry. So, once you've spotted a reaction, the next step is to actually describe it. And to do that, well, we need to learn the language. I mean, think about it. We could say something like, when a strip of magnesium is burned in oxygen, it turns into a white powder called magnesium oxide. But, wow, that is a mouthful. It's just too long and clunky. Scientists, they need a shorthand, a much more efficient way to get the point across. So, the first step is what we call a word equation. It's super simple. You just put the things you start with, we call those the reactants, on the left side. Then you draw an arrow, and on the right, you put what you end up with, the products. Magnesium plus oxygen gives you magnesium oxide. See? Way cleaner, right? So much faster than a full sentence.
But we can do even better than that. By swapping out the words for their chemical formulas, we get a chemical equation. Now, this is powerful. It's way more concise, and it's just packed with information. Mg for magnesium, O2 for oxygen, and MgO for magnesium oxide. But, there's a little problem here. This equation, it's not quite right yet. We call this a skeletal equation, and it's actually breaking a really, really important rule.
Moving on to section 3, the rules of the reaction. See, every language has grammar, right? And chemistry is no different. To fix that skeletal equation we just looked at, we have to follow what is probably the single most important rule in all of chemistry.
It's called the law of conservation of mass. And what it boils down to is this. You can't just create or destroy atoms out of thin air during a reaction. It's impossible. Whatever atoms you start with, you have to end with that exact same number of atoms. The books, as they say, must always be balanced. And this is exactly where our equation for iron reacting with steam just falls apart. Take a look at the table. On the left side, the reactants, we start with 1 iron atom. But on the right, the products, we somehow end up with 3. What? And we start with 1 oxygen atom, and it magically turns into 4? No way. This equation is breaking the law. It's completely unbalanced.
So how do we fix it? We balance it. And the method is kind of like solving a little puzzle. It's often called hit and trial. Now, the most important thing to remember is that you can't change the formulas. H2O is always H2O. You can't just make it H2O2 or something. But what you can do is change how many of each molecule you're using. We do that by putting these big numbers, called coefficients, out front. We just tweak those numbers until the atom count on both sides is perfectly equal.
And there we go. Look at it now. It's perfect. 3 iron atoms on the left, 3 on the right, 8 hydrogens on both sides, 4 oxygens on both sides.
Now the books are balanced. The law is satisfied. And this equation, this balanced equation, finally tells the true story of what's happening. All right, next up, section 4, 4 essential reaction types. So now that we can write and balance these things, let's check out the main genres of reactions. Yeah, just like stories have genres, so do reactions. And grouping them helps us predict what's going to happen.
So let's start with two types that are basically opposites. First, you have a combination reaction. This is where two or more simple things come together to form one more complex thing. Think of it like A plus B gives you AB. Like when you burn coal, carbon and oxygen combine to make carbon dioxide. Then you've got the opposite, decomposition. This is where one complex thing breaks down into simpler parts. AB breaks apart into A and B. It's like a single compound just shattering into pieces.
Okay, next up are the swapping reactions. A displacement reaction is kind of like someone cutting in on the dance floor. You have a more reactive element, in this case iron, that just swoops in and kicks another, less reactive element right out of its partnership. But in a double displacement reaction, it's like two couples showing up and just swapping partners. They both exchange ions and form two completely new couples, two totally new compounds. Now, running underneath a lot of these reactions is a really important process called oxidation reduction, or just redox for short. The easiest way to get your head around it at first is to just think about oxygen. If something gains oxygen, we say it's been oxidized. If it loses oxygen, it's been reduced. This simple transfer is honestly one of the most fundamental ideas in all of chemistry.
Okay, last section, number 5, chemistry in your daily life. So why should you care about any of this? Because this stuff isn't just happening in some far-off science lab. It's happening all around you every single day. Let's bring it all back home. Have you ever seen a rusty car door or a nail left outside? Or maybe some fancy silverware that's turned all black and dull? Well, what you're looking at is corrosion. And now you know the secret. It's just a slow, steady oxidation reaction. That metal is just losing a long, slow fight against the oxygen in the air.
And you know that kind of gross, stale taste of old potato chips or crackers? Yep, that's rancidity. And guess what? It's the exact same chemical process we've been talking about. The fats and oils in the food have been oxidized. This is actually why chip bags seem like they're half full of air. They're not. Manufacturers flush them with nitrogen gas to push all the oxygen out and stop this reaction from happening. It's all chemistry.
So, look at what we've done. We've learned how to spot a reaction, how to read its language, and how to understand its basic rules. You seriously have the tools now to see the world not just as a place full of, well, things, but as a place of constant, predictable, and amazing transformation. So the only real question left is, what reactions are you going to spot out there today?